Let me show you a single hardware change that slashes the size of the rulebook by half, using just one chip. In two concurrent video series, the Commodore 64 from scratch and the ZX Spectrum Turing Edition, I'm using a modified form of a Turing machine called a Random Access Turing Machine as the core CPU. The reason? To show, in hopefully a very simple way, that the principles Turing proposed nearly 100 years ago can still guide modern CPU design. Let's start with the basics. We all learned about column-based addition in primary school. You have a notepad with digits and a rulebook in your head. Add the digits, write the answer, carry the 1 if appropriate, and repeat. Turing formalized this with a machine that had a rulebook and a notepad, which he called a tape. In practice, we also need a state to track where we are in the rulebook and somehow of knowing where we are on the tape. But Turing simplified the notepad. Instead of a two-dimensional page of paper, he made it one-dimensional. And instead of jumping around, you only move one symbol left or right at a time. With enough creativity, it still works. In hardware, here's how it maps out. The notepad is a static RAM chip. The location is tracked by an up-down counter, our tape head. The rulebook is a large EPROM, and the current state is stored in flip-flops. To determine the next rule, we use the current state, which is 13 bits, and a symbol read from the static RAM to address the EPROM and fetch the next rule. On the positive edge of clock, the new state, write symbol, and control signals are latched. Then, and only then, we write the new symbol onto the tape, and then move the tape pointer left or right. Now, believe it or not, I built a machine like this, and it works. Here's my pure Turing machine, emulating the 6502 with just 2-bit symbols. Yes, that's Apple II Pac-Man. Watch closely. Look, Pac-Man just moved. Why is it so slow? Because it takes over 1 million clocks per instruction. Every time we want to access a byte in main memory, the tape head has to step over each location one by one to reach it. This sequential access kills performance. To fix this, I made a small architectural change. Instead of a counter stepping across memory, I now store the tape pointer in static RAM. I used this value stored to drive address lines to another memory chip, the main memory. We still call this the notepad, but now it has a notepad SRAM for the tape pointer and a main memory for the actual data. This gives us indirect addressing, a key step towards Turing completeness and a full CPU architecture. And here's where it gets fun. If the tape pointer is replaced by a program counter and the address can jump arbitrarily, then the finite state machine can jump to any location in memory instantly, not step by step. This is why I call it a Random Access Turing Machine. In my opinion, this is the single most important innovation in computer architecture, period. I asked ChatGPT about this, and no surprise, it agreed with me. Although I've noticed Chat tends to agree with me a lot. The original pure Turing machine took about 3 million clocks per instruction. The Random Access Turing Machine with optimization takes about 7 or 8 clocks per instruction, and the original 6502 itself, well, that's 2.5 to 3 clocks per instruction. That's a 400,000-fold speed up, or by allowing the finite state machine to jump around instead of stepping out one cell at a time. I called this 8-bit version of the Random Access machine the Turing6502, and it took nearly 8,000 rules, each with 256 symbols. That's around 2 million EPROM locations. That's why I used two 27C322 EPROMs, giving me 2 million addresses, where each address contains a 32-bit wide word. And even then, the rulebook barely fit. One of the reasons it ended up so large is how I handle data transfers. In the Turing6502, the notepad static RAM stores everything. The visible registers, such as the accumulator, index X, index Y, stack pointer, program counter, and status register, but it also stores a number of hidden registers, like the ALU's B register, the instruction register, and 2 16-bit effective address registers. So the notepad static RAM becomes a full register store, directly addressed by the rulebook. Now, Turing's model says we need to read a symbol and write a symbol at the same location, So in my design, reads come from either the notepad or main memory static RAM, while writes always go back to the notepad static RAM and optionally to the main memory, depending on the control signals. Let's look at two examples. Say I want to store the value of A into some memory location, which is what the STA instruction does. I want to transfer the value of A from the notepad SRAM into the main memory SRAM, and we'll assume that we've already set up the memory address registers. All the rulebook needs to do is read A from the notepad static RAM, then write the same value back to both the notepad SRAM and the main memory SRAM. Simple. Just one rule required. That's sufficient. Example 2. The TAX instruction. Now, if I want to copy A to X, it's more complicated. I have to read, then write back A, and embed the value into part of the next state. Then, in the next cycle, I then read X, ignore it, and write back the value that was embedded in the state, which corresponds to the value of A. But A can be any number from 0 to 255, meaning I need 256 unique states for the transfer to represent all the possible values of A. And with only 8,192 states available, that means I can only do this kind of transfer 32 times before the EPROM is full. That's a huge cost, all just to copy one register into another. This file shows the starting state for the various state machines in the rulebook. Just as an aside, I tend to use the terms rule and state interchangeably, and these values are all in decimal. Here, for example, you can see the transfer A to X instruction. This starts at state 882 and runs through to state 1139. Remember, this design allows for a total of 8,192 states. States 882 and 883 set up the instruction. Then state 884 is TAX when A equals 0. State 885 is TAX when A equals 1, and so on. All the way through to state 1139, which is TAX when A equals 255. Let's scroll down. In this case, the last state used was 7,611, and that doesn't even include the Pac-Man loader, which adds another 300 states. That brings the total up to near the 8192 limit. In fact, for some of the arithmetic, particularly additions and subtractions, I had to fall back to 4-bit mode just to make it fit. It's slower, since it takes extra clock cycles, but it cuts down the number of states required. Some operations are particularly expensive. Jumps and branches take 900 states. JSR and RTS both use 500 each. The addressing modes collectively burn through around 1400 states. It's even worse for the Z80. These move instructions alone would blow the EPROM budget. To solve this, I've added a simple 8-bit transfer register. Just an octal D-type flip-flop with an output enable. It's clocked on the negative edge of clock, so it always captures the last value written by the finite state machine. It's connected between the data bus from the static RAM and the data bus connection to the EPROM. I have another chip here wired up in parallel, which is to speed things up, but I'll go over that in more detail in a later video in the series. This other chip is actually a 74HC373 transparent latch, hardwired for transparent mode. For now though, you can think of it as being a buffer with an output enable, a bit like a 74HC244. When clocks load during the read part of the cycle, using a control signal from the rulebook, I can select whether the EPROM sees the output from one of the SRAMs via the buffer, which is normal mode, or the value stored in the transfer register. So here's how we optimize the transfer of A to X. Read A from the notepad SRAM. It goes through the buffer and onto the EPROM, and then it becomes the output symbol. Next, when clock's high, we write this value back to the notepad SRAM A register, but here's the important bit. It also gets latched into the transfer register. We then jump to the next state, but there's only one possibility, not 256. Read the value from X, but this time, instead of reading the actual value of X, the EPROM rulebook sees the value in the transfer register. The actual value of X is ignored. This means the EPROM is really seeing the value of A and not X. When clock goes high, this value gets written into X in the Notepad SRAM. Instead of storing the value as part of the state, I store it in the transfer register. The end result, what used to take 256 states, now takes just one. Now, here's the real payoff. This is with the transfer register in place. Take a look. Most of the transfers now are just 3 states. That alone saves 1,500 states. Stack operations are down to 7 states each, saving another 1,000 states. JSR and RTS, well, now they're just 25 states each, for a total saving of over 1,000 states. The only outlier is the take branch path, which still needs about 270 states because it includes an 8-bit addition. Same for the addressing modes, like 0-page offset, absolute offset, indirect Y-indexed. These all still rely on 8-bit math. In fact, I think X-indexed indirect even drops down to 4-bit addition just to make it fit. So there we go. With just a single transfer register, the rulebook drops from over 7,600 states to just over 3,000, and we haven't compromised functionality. In fact, the machine still runs Apple II Pac-Man, and in the ZX Spectrum Turing Edition, this change alone was enough to eliminate an entire EPROM. What's exciting is this is just the beginning. In the next video, we'll try something a little bolder. We'll add a dedicated arithmetic logic unit. At first glance, that's just to clean up additions and subtractions and reduce state count, maybe save a few clock cycles. But as we'll see, once you introduce an ALU, a few other optimizations start to fall in place. The rulebook doesn't just get smaller, it begins to take on a very different structure. We're not quite ready to unpack that yet, but let's just say the ALU might turn out to be the second most important change to the basic Turing machine after random access memory. So, if you're curious where this architecture is headed, stick around. We're about to start reshaping the rulebook itself.